Am I audible? Yeah, okay. Hey everyone, good afternoon. I hope all of you had good lunch. We will try to keep this very interesting because it was something of something that we built out of interest more than anything else over the past 6 months. I'm Nischal. I'm the VP of Engineering at Omnius, a Berlin-based AI startup, and Raghotham will introduce himself.
Hi. Am I audible? Yeah. So I'm Raghotham. I work for Ericsson Research back in Bangalore, India, as a senior data scientist. And before this, both Nischal and I, we have been working with a bunch of big enterprises like SAP and then a bunch of startups. We also used to have our own boutique data science consulting firm. And we helped a lot of small and medium businesses build their data science stack from the scratch. So during this while, we've also been very active in the community, and we are speakers at various PyData and PyCon conferences around the world. And so deep learning for fonts was one such idea that came out of interest. In 2016, both of us, we were talking at PyData London, doing a workshop on deep learning. And one of the things that caught our interest was the beautiful font on the London bus boards. Like they're super crisp, clean, you see it from far away, they're so neat. So we were intrigued to know which was this font. And then a quick Google did not return the results. Then we have to go through few forums and then Wikipedia page. And we got to know that this was Johnston 100 font. And that's how we figured out this is the font. But then there always remained a thought as to, isn't there a service on the web where you can simply click a photo, send it, upload it, and figure out which font that is? So obviously, we always have this thought process of, if we have thought about this, maybe someone should have already thought about it and built something like this. And we figured out that there are a bunch of services like what the font is one of them. So you can give an image of text, and then it'll throw you what are the possible fonts. And so this image here on the left is the test image we gave it. It's a Leto font we used. But then if you look at the results, you don't see Leto anywhere. So the results were not as expected, right? And then we figured out there was one more tool called as what font is. Again, we gave it the same image. It's a Leto font. It said the image is very complex. Please give a smaller crop. And then I gave a smaller crop of that, and it says it is still complex. I cannot comprehend. Right? And then there is one more service called Maturator. I think Maturator is one of the more decent services where that was the closest in terms of results. If you look at it, it did detect, it also asked me to crop the image. I did crop it. And then the first one was a sponsored result, but then the second one is PT Sans. Not exactly Leto, but then yeah, it was somewhere close. It is somewhat similar at least. So we also figured out there are a lot of forums where people go upload an image, and there are a bunch of people who say, okay, this is a Leto or different fonts, right? That's the thing. So we figured out that, and we figured out that there are problems that designers or any person using it, there's no service available which is accurate. And then with that, we started Fontastic. And being deep learning practitioners ourselves, we thought that why not build a first-class font classification service, host it on web, where the aim is we want to do two things with Fontastic. One is have a font classifier where anyone can shoot an image and upload it, return what is the font, what is the probable font that is, right? That is one. But also this is not just aimed towards designers or others. We want people from different background to understand how deep learning works. So with that in mind, we also want to build a lot of visualizations and demonstrate how deep learning works, why it works, more like see through the network and see why it works and how it works. So do a lot of feature visualization and help people with different background. It is also very important for deep learning practitioners or data scientists also to understand why a model works and why it doesn't work. And it is just to analyze the features, help it protect against adversarial attacks, right? So that is also very important. So these are the two things with visualization. One is build a classifier and visualization. And Fontastic is also part of a bigger project we are working on called Deep Learning for Humans. With this, we want to work on multiple such mini projects. So Fontastic is one where we deal with image data. So we want to do the same thing with audio data, then time series data, maybe structured data, and so on and so forth. So that's what we aim to do at. And all these projects are our fun projects, and we want people from different background to understand how deep learning works. It's all open on GitHub. We would love if any one of you would like to contribute. Yes, please do that. Yeah. So that's about deep learning for humans. Coming back to the agenda, we'll have these three things we'll be talking about today. One is data acquisition, what goes into starting a project, building model, and then feature visualization. So data acquisition, like any other data science problem, we had to acquire data. So we searched online. There are no data sets where you have off-the-shelf images where you could simply download and build a classifier on top of that. So we spent a lot of time just to get the data and get them in the right construct. So there are different sites which has font sites, right? There is font Squirrel, there is the font, there is Google Fonts, and most of the new fonts are on Google Fonts. The problem with Google Fonts is that while it is a very pretty website, the content there of the font rendering is not an image, it's a text field, which means it's become very hard for us to scrape, and the entire data pipeline becomes so hard with that. So we skipped Google Fonts. The first try was font Squirrel, and this is how it looks. When I go to Roboto, they have different specimen images of different size. So basically, the top image is one, then penultimatum is a different image. They're different size images. And we started scraping that. We had a first pass of the scraper return, and we analyzed the results, and we saw there are two problems. One is the images are of different dimension. Some of them are wide, some of them are tall, some of them are square. And it's very hard for us to normalize. While we also did normalizing them, even with normalizing, we ended up with just like 10 images for every font. And with that, you can hardly build a good classifier. So then we were stuck with the data acquisition process. We said, okay, let's look at different alternatives. And there is thefont.com. This is a very pretty website. So the advantage with thefont.com is you see that you can add a custom text there. And once you start adding a custom text and hit submit, you see that the custom text can be actually passed as a query parameter in your URL. So with that, all we have to do is pass random text and get new set of images. But we realized there are problems with these two. With this data, the font.com does not support all new fonts. For example, Leto is missing, or Oswald is missing. So all the new cool fonts are missing. Most of the fonts which are on Google Fonts are missing here. And then again, these are only wide dimension images. Again, normalizing them is hard. And the intended use case would be you randomly take a screenshot or take an image and then pass it to the classifier. And it does not support the dimension, basically. So these were the problems. With this, we were like totally lost. running out of all the options. All the font website has some problem, not enough data. And Nischal and I got on a call. We were like thinking, what's happening? Maybe we can't do this. And then we were Googling, and then we figured out that there is a forum, there was a blog post which said that with the Python pillow library, you can generate images locally on your computer. You give it some text and a font file, a TTF file. You can generate an image of desired dimension. So this was something very nice, and we looked into it, and this was something promising. With this, we really cracked the data acquisition process. So what we did is we took 4 bunch of random text, and we created 4 layouts for them. With 4 random text, what we did is we generated 4K images. So every text layout is a 4K image. With this 4K image, now we take 256 by 256 size random crops. Yeah. So you have a big 4K image. We take smaller random crops of them. And it's not just random crop. We also do a lot of random scaling, random rotation, random zooming, so that from day one we know that while we are preparing the data, we don't overfit our models to the data, because deep learning models are prone to overfitting data very easily. So we made sure that from day one we build our data pipeline in such a way that we don't have any problem with overfitting. So I'll show you examples. And the advantage with this was we control the input text, we control the dimensions, and we also control what is the font style, what is the font size, and we have infinite amount of training data available with this. So let's look at what a 4K image of a font looks like. This is one of the sample images. This is a 4K image. And then we take a 256 by 256 random crop with random zoom. This is how it looks now. So we take 10 of them, and we do it for all layouts. Basically, this is how it looks for one of the fonts. So if you see that there's randomization in layout, in the font style, in the font weight, and there is random zoom. So the deep learning model should not just look at where the white spaces are and say classify this as a Lato or Open Sans. So we have made sure that data is pretty diverse that way. So with this, we had really nailed the data acquisition process, and we set on to build the first set of models. And we always, coming from an engineering background, we always try to break down into smaller problems. So we decided that we'll do a feasibility check of how good the model is and what would be the accuracy we'd be looking at, because this is very important. Coming from a consulting background also, it's very important for you to do the feasibility check and do a POC and understand, okay, I'll not take the entire data set, I will take a subsample of that and then see what are the metrics we are looking at, what are the KPIs. This is what we go behind. And to do that, we use the FastAI library, and we built our initial set of models. Today, deep learning models and frameworks have come to such an extent that with just 3 or 4 lines of code, you can do a very good POC and analyze if you'll be hitting good enough accuracy or what are the problems in the entire data pipeline, the output, all these things. So this is a sample code. So all the content is on GitHub. We have separate notebooks for each and every experiment we have built. But this is just like a high-level bird's view of how it looks like, right? So with this, we know that with 6 epochs, we are looking at 92% accuracy. And the confusion matrix looks something like this. This was just for 6 font classes, and it looks promising. You see that most of the times it works. And with this, we set on to build the next set of full-blown model for all the 70 fonts.
Okay. Thank you, Raghotham. So why PyTorch? And you would probably guess what we want to do with PyTorch, and there are 70 fonts that we want to work with. Why not do FastAI? So there are okay, is this no?
This one. Okay.
The reason why PyTorch is, and of course this gets a little borderline scandalous in different conversations that we do, is it's very easy to read, it's very easy to write, and it gives you the flexibility of customization of adding things that you would want, and also gives us the capability of extracting information from the networks to pass into visualization frameworks. And one other cool thing with PyTorch that we've seen is the interoperability between scientific packages in Python, like NumPy, SciPy, and whatever you do. You can work with PyTorch very easily at that level and interchangeably use the libraries as you can. And when we started working with this, we decided we look at various kinds of networks, and I'm talking about ResNet, Inception, and all the other bigger networks that we wanted. And we decided, look, we are trying to do this project for two reasons. One, we want to solve the problem for sure. And two, we need to understand why this network works. And that's the whole idea behind deep learning for humans. So we decided we'll use the smallest possible model, and we see how it performs with the baseline score that we generated from FastAI. So we started with a ResNet 18 and not even a 50. And for those of you who are not aware of what a ResNet is and how it's different from other computer vision models, you will see Inception, you see a lot of other networks. A few years ago, everybody in the data science community and deep learning believed that you stack a lot of layers and basically a problem is solved. However, what they started seeing was that at a certain point in time, it doesn't work, and they didn't know why it was not working. And when they started looking and removing a few layers and they started seeing what was really going wrong, they came to the conclusion that if you keep stacking up layers and you go deeper and deeper and deeper and build these big models, you end up actually losing track of what you want to solve. So there's this problem of vanishing gradients where you don't really know what you're looking at to solve at a certain point in time. And they decided, look, if this is the situation, what if we provide for blocks of layers, after the output of a layer, again the input, so that we have the information of what we want to solve, and we also have information of what the networks are doing, and combining this, you pass in as an input to the next block. And this gave to ResNet, and if I'm not wrong, this came out of Microsoft Research Lab, and this was a big win because this basically gave a boost in the computer vision thought space of solving problems with big data sets and not having to build big, deep networks, right? Why pre-trained models? Why not build a custom model ourselves? And what is this transfer learning that everybody is talking about, right? You could always build custom models yourself, and building models more than science is an art. So you really need to know why you're putting layers, what's happening, what's going on between. But not every time this is required. A lot of times these models are capable of solving problems, and they've been trained on larger data sets. Now, what is transfer learning? So before we go into the theory of transfer learning or what it actually does, there's biological influence on how transfer learning came about. So when we were kids and we started running around, we really learned how to run. And when we started playing soccer, we did not have to learn about running again. We just had to adapt how we ran with a ball at our feet. And that's what transfer learning essentially is about. It's about learning to do a certain task and using this information to solve another task in the relevant space. And relevant here is very important because if you train a network that understands how to classify images and you use this network as a pre-trained model to understand speech recognition, it's not the same because it's completely two different domains. And just because you do transfer learning, you have a pre-trained model, this is not something that would work, right? So that essentially is transfer learning. Transfer learning is the capability of using an already trained model and then training it on a specific task in a related field to solve it. So this is what it would look like. So you have a random neural network, and here think about something like a ResNet 50, ResNet 18, And this is being trained on a very big corpus of data, the ImageNet. And for those of you who have not seen what this is a very good data set to train your computer vision models on, or use a pre-trained model that's already trained on ImageNet. Once this is done, you take your specific problem and then you fine-tune this network and the learning that it's doing to solve the problem that you have at your hand, right? Now, does this mean that you take pre-trained models, you take something that it's learned on, do transfer learning, and it works? No, it doesn't. So this is where things start to get quite interesting. So we talk about hyperparameter tuning, and if you go on the internet right now and just type hyperparameter tuning, you get about 3 million hits of pages of what hyperparameter tuning is about. We will try to deconstruct this into something that is one of the most important things for hyperparameter tuning, or one of the important aspects, and that's learning rate. Now, what is learning rate? If you think about deep learning networks are nothing but stacked hidden layers that are doing very simple mathematical functions. They're just stacked at various levels, trying to understand what is the problem and what they're trying to solve. Now, that is why people say deep learning is a black box. It works, but we don't know why. And over the last few years, a lot of time has been spent on deconstructing this. And one of the things that computer scientists realized was, as humans do, everybody has a different way of learning and a different velocity or speed at which they learn. And that's the same thing with networks. Now, a deep learning network essentially at the end of one pass or one epoch is comparing the results that it's predicted to what the actual results have to be. And when it tries to do this, what it thinks of is, okay, now the results have deviated from what it is supposed to be, and the only thing that I can change now as a network is I can't change the architecture on the fly, I cannot change my input on the fly. The only thing that I can truly change is to understand what are the features that I have picked up in this network that's landing me here. And when you look at these features, they are nothing but a weight matrix, and this weight matrix has to be optimized to give you the results that you're looking for. Now, how do you optimize this weight matrix? And that is where learning rate comes in. Learning rate is a factor of figuring out how much of this weight matrix you want to change in order for you to get to your solution. And this also lands up in the situation where you have a global maxima that you want to get at, and you have local maxima of where you want to be. Learning rate changing. So learning rates are usually quite small in nature. They are operating anywhere between 0 and 1. So if you think of your weight matrix as an m cross n matrix, your learning rate is nothing but a small multiplying factor on this. So you would consider, if you take a very simple equation where x is equal to your weight matrix Wt, it gets multiplied by a small factor of learning rate. So it is Wt into 0.001, 0.1 based on what you would choose, and this is operating between 0 and 1. And the plot here is quite interesting because on the y-axis, which is the loss, and the x-axis, you have different learning rates. And you see that for different learning rates that we are using, there's not much of a difference between 10 raised to the power of minus 6 to 10 raised to the power of minus 4. We see that when we are running with this, the loss slowly starts to reduce, and we realize at 10 raised to the power of minus 3, our loss function is really our loss is really reducing. However, if we get quite aggressive and we say, okay, if 10 raised to the power of minus 3 is good, then 10 raised to the power of minus 2 has to be better, and 10 raised to the power of minus 1 has to be much, much, much better. But that's not the case. It's because if you get too aggressive, you tend to jump out. So think of a car going down ditches, going down a hill, and if you accelerate too much, you might actually jump off the cliff. So if you want to remain on track, you need to maintain your momentum, you need to maintain your acceleration, and that's what learning rate's all about. There are various ways to work with learning rate, and this introduces a very important concept called as learning rate scheduler. So as you see from this plot before, as a normal person who's working with a problem at hand, how would you know what is the appropriate learning rate to choose? And learning rate scheduler actually helps you get there. So what learning rate schedulers do is they take between your maximum learning rate and minimum learning rate, and they sort of change during the training of the network. So they take different learning rates as and when you're learning through the process, thereby helping you get to a global minima and not pushing your car over the cliff, right? And this is a small code snippet, and we've put detailed instructions on what this means and what it does on GitHub as well, and you can go check it out on what the learning rate schedulers are doing. At the same point in time, if you look at the last 2 lines there, the entire idea of deep learning is built on the concept of stochastic gradient descent, and we use stochastic gradient descent and we use a scheduler on top of it. Now mathematics is all about optimization, and at a certain point in time over the last few years, computer scientists have spent a lot of time on understanding if we can optimize this itself. So if you go and start reading about deep learning networks, you start reading that ADAM, RMS prop, all of these other terms start coming into place. So what these optimizers are, or criterion are, is they do a combination of your learning rate scheduler and your optimizer put together. So what this means is the network or the function starts to become smarter to adapt to different learning rates by checking the output and what the input is and how they work with the weight matrix. Now this is where it got really interesting for us. Is we said, okay, if we don't use a learning rate finder, we don't use a scheduler, what happens then? We trained our ResNet 50, we ran it for 40 epochs for about 15,000 images belonging for 70 classes, and overall this was our F1 score. And we said, look, if our baseline score on 6 fonts with fast AI was 90.94, we have to figure out how to get this to work without having to change the network but tuning the hyperparameters. And then we added our learning rate finder, we added our scheduler, and this was the result. So if someone tells you, or if you start working with your deep learning networks and you start thinking, I'm going to add a lot of layers and my network will just get better, please don't do it. Take the smallest possible network, understand what's happening, and play around with your hyperparameters. The final aspect of deep learning for humans that we want to kickstart is a lot of us who want to work with deep learning networks, who want to understand what deep learning networks are not essentially from mathematical background. So when you open up scientific papers, you open up blogs, there are these mind-boggling equations that are there and you don't really know what's going on, which is why we decided if we were to do this, the most important aspect for us would be visualization. Now, what is feature visualization? Feature visualization is a way to understand what the network is actually learning through understanding through concepts like GradCam analysis. So what GradCam analysis really does is it's a part of this bigger project called as Activation Atlas. Okay, I think just yeah. So we want to understand what the network is learning, right? And in the 0th layer, you see that this is just the beginning, and then you go to the first layer, you slowly start to see here that this layer is starting to learn the curves of the font, right? And then when you start seeing this layer, you start to see that it starts to emphasize on the curves of the font. It starts to look at what it should learn and what it should ignore in order to classify this appropriately.
So this is more like a heat map on top of your input image. So wherever you see the reds, those are the places where there is highest importance in that layer. So when you pass through the layer from 0 to 1, you see that the reds are moving here and there.
Yeah, and what you also start to see is in the first layers, the network is really looking at the smaller aspects of the image, and as when you gradually increase the layers, they start to look at the bigger part of the image. They're learning. So the initial layers in the deep learning network is usually trying to learn the smaller features, and the higher up you go with the layers, they're trying to generalize and look at the problem in a with a bigger size. Yeah, and
again, this changes with every epoch. This is just for the first
epoch. Yeah, and if we just take this layer and we look at what changed during the epoch, you start seeing the network starting to play importance based on what it should really learn and what it should start ignoring. And at a certain point in time, you see that it stagnates. Yeah, and this is something that it's quite essential in understanding what deep learning networks are trying to do and what they're good at. Activation Atlas, and and this is a very big post that's been running around for quite some time, is a very cool project around visualization and feature inversion and understanding what networks are learning not at the end but at every single layer, and it's a combination of every single neuron in this layer. So this is a very nice example. On the left here, you can see that there's the classifier classified the image as the gray whale, but we superimposed a baseball glove with a baseball in it, and then immediately it thought it was a great white shark because there's a white image there and there's a shark there, and it sort of started to combine. And this link here actually explains what the network is learning. And the funny part is the fourth prediction is a sombrero, which is simply because of the fact that the baseball glove is brown in color and it looks like it's hollow because of the baseball that's there, and it assumes to be a hat. This is quite interesting, and we want to bring this more into our project where you understand what the network is really trying to do. Over to Raghotham now to put some emphasis on how we actually achieved doing this project.
So, as you know, Nischal works in Berlin and I work in Bangalore back in India. And then we are 5,000 miles apart, there's time difference. We only get weekends to work on side projects. So it's very hard for us to, figure out, for the other person to figure out what's working, what's not working. So today, luckily, we are in a position where we have good collaboration tools, like we can get onto a Zoom call and then figure out things. But then given that we are in different places and we have our own priorities and things to take care, it's not always easy for us to get on a call. So we use things like Notion, where you can have everything in one place. Just have a task board, just have all your notes there, and then notify the other person saying this works, this doesn't work. So yeah, remote works really works in such cases, and especially when you are doing a open source project, you have to be well equipped and come up ground up with all these resources. And like we said, this is an open source project, not just Fontastic. We also want to work on different media. It's not just images, but also audio and different things. So please feel free to contribute. It's not that only 2 people can do this. We need more people who can bring in that awareness within the deep learning community. It's really very important. So yeah, that's about Fontastic. You can reach us on Twitter, GitHub, anywhere. And that's the URL for the project.
Yeah.
Thank you.
Yeah, we're open to questions. I think we still have another 5 minutes.
To acquire the TTF files for the fonts, do we have some repository or
Sorry?
To get the font files, to generate the data, the images at the beginning?
We have everything on the project.
So you have everything on the
Yep.
project already implemented?
Yeah, so I think
Can maybe
yeah, it's on GitHub.
You can just exit the presentation.
Yeah.
Yeah, for those of you who didn't hear the question was if all the font files, the data, everything's, if it's available. Yeah, we've put a README file with links to the TTF files, and we also have built the project in a way where you could take these TTF files and you could run the entire data creation yourself. So it's not just IPython notebooks. We have a proper repository of code with commands that you can run, that you can point to, that you can build. And we've also added experiments and stuff, so you can change some hyperparameters and everything.
Yeah. Yeah, so this is basically the project. So we have a Fontastic module inside which you find that there is a data generation submodule. So just run them and then I think you're good to go. Even the README has the link to the zip file of the TTF file.
Yeah, so we have about 70 fonts that we are supporting now, and the idea is we put this as a service with also people have the capability to upload images, and we'll run through an object detection layer first to find out where the text is and then pass that text through Fontastic. So
because what we have today does not work for text in the wild. I cannot simply shoot something and then use it. So like Nischal said, we need object detection on top of this, which can do that for us.
Anybody else? Any questions? Okay, cool. Yeah.
So have you tried it like with more real pictures? Because the testers like generated images.
Yeah, so that is what I told about. We have not tested with text in the wild where I can simply take something and then it works. No, it does not work still. So we are in the process of completing this. So we'll have to add object detection on top of that, take a crop of that text and then run the classifier on top of that.
However, if you manually crop the image and then pass it to the network, we've seen it to work quite well.
Yeah.
So for at least the 70 fonts that we support, it provides a confidence score for the prediction that it does. And we want to expand this to as many TTF files as we possibly can.
At the moment you don't add any noise?
We do. So we do some augmentation of data. So we're adding noise, we're doing shear, we're doing some rotation, transformations in the way we do the data loading itself. So the network is trying to learn different types of orientation of text and some noise and some of the transformations that we introduce. And hopefully we can add a lot more noise and samples for us to be able to work in the real world. So that's the next steps that we want to work on.
So we have the entire transformation pipeline itself on the notebooks itself. So if you have a look at the GitHub repository, I think it gives you an overall view of what's happening there.
Okay, cool. Thank you.
Thank you.